control areas. In the national view of the India, the energy generation, transmission, distribution, and control, we call it as one grid. In that perspective, total energy sector in the country is divided into 5 control areas. You can just see the Indian map has been colored with the different colors to identify what are those regions, what are those control areas which we are trying to correlate with this example. So the north region, which is with the greenish color, is having one zone control periphery, which is responsible to generate electricity, deliver its end user, and to keep transaction from that region to the neighbor region by tie lines. Similarly, we have north, south, east, west, and northeastern. These are the 5 reasons for the appropriate operation of the power system control in the continent, in the particular country perspective, is divided according to the resources available and control exercise. Being the main control being at Delhi. Delhi being the National Energy Control Center, which supervise all these control areas being central to that. What is happening in the northern region, southern, eastern, western, and northeastern is centrally monitored by National Energy Control Center at Delhi. And when I combine all together into a map, it becomes connected map by states. Then each state has State Energy Control Center, SLDC, State Load Dispatch Center, SLDC. Then each state is again divided into areas. Like in our Karnataka, HESCOM is the one, BESCOM, other regions. Like that, we have ALDC, Area Load Dispatch Center. Likewise, segregation of the total country's energy generation perspective is outlined as control areas. Once we regionalize it, suitable control exercise, monitoring, and execution is possible having supervised the specific area for the adequacy of control. Having viewed the controlling aspects, features, resources in the northern, controlling of generation aspects at northern region is superior. So that focusing on that it is being done. So likewise, regions are segregated. Each region is interconnected for the transfer of power. We call it as exchange among the regions. We are looking forward with the tie lines. Tie lines are the infrastructures laid between energy corporations for the profit of trading of power, to sell or to borrow the power and to connect. Altogether, when I have a control area, which is a northern, which can be shown you in the right side picture. A dotted circle or a elliptical in fashion may have a generator, may have its load. There is a common control signal emitted from the automatic generation controller installed in that area, supervises all the generations, control, measure all the outgoing powers, and take account of area's error. Do this control area is fulfilling its area requirement as well as its commitment for the selling up or borrowing of power from that area. That is monitored by the central controlling agency like automatic generation controller instituted inside this controlling periphery. You can imagine this one mechanism, we call it as a control area, a area encompassing boundary. Till that point, common signal radiating from this controller keep reaching and acting on the points. So this is the common controller keep controlling the connected devices in this periphery boundary, and later it has no actions. This reason being a part of a power system, till that point of encompassing boundary, signals from the controlling center or energy control center keep reaching for the appropriateness. In that respect, I can say this north region, south region, eastern, western, northeastern can be visualized as control areas. Definitely, when there is a control area, it should look for its requirement stability first. Then these regions are segregated into areas. Why not the only one? Because controlling aspect become very difficult. Hence, segregation into different areas become very superior in operation of individual area because area being limited. Hence, it become very easy. Later, interconnected operation among the areas is visualized. Then tie lines facilitate to transfer the power from one area to another area. So these blue lines which are being shown, we can visualize them as tie lines, radiating transmission infrastructure between region to next region to another. This way, national grid is connected to one another. So we say one grid, so one frequency. This is how all the generations from the northern to southern, eastern to western and northeastern are interconnected one to one, such that common potential and common frequencies made into action. Therefore, it's called one grid. So there is an exchange of power from one to another within the region for its stability point of aspect. Therefore, once this is visualized, I have an example for you how control areas can be visualized. Next, being control area, we learned something called as area control error. When is that individual control area is in stable mode of operation? Whatever the transaction this area is trying to do, is it developing adequate megawatt power and meeting the requirement of an end user? When is that? When all it is not able to do, it become a question. Then how that is being computed in the energy control center, that is called energy generation or automatic generation controller algorithm compute a error. Is that error of a locality is 0, is it plus, is it minus, like that? That is called as ACE, area control error. What is this? Let us see once again. So I have a concept ACE, area control error. The automatic generation controller algorithm or a program running in the energy control center of a control area look for ACE. ACE must be always 0. The control area, energy control center, dispatcher, scheduling concept should be such a way focusing all the time to see to it that ACE, area control error of that locality is always 0, maintained close to 0. If it is 0, what do you mean by whatever is the generation right now that area is doing? Whatever the right now loads which are absorbing and whatever the transaction this area is doing with the neighbor corporation are in perfect balance. That state indicates the ACE being 0. But it's very quite difficult to maintain ACE 0 because when an area is connected to it itself to meet the load, it can manage very easily. When the neighbor states are demanding and delivering power to the neighbor state, when any contingent variation in that neighbor to whom you are agreed upon to deliver the power, there is an increase or decrease of requirement. Then definitely that increase or decrease will demand your generations to change the set point. Due regard to that, there will be a change in frequency, change in controlling and all. Error won't be 0. Therefore, very dynamically, there could be an adjustment of ACE to 0. Therefore, this is to be understood. For an area to be steady state, area control error must be close to 0. Then how to understand, how to evaluate ACE of an area then? ACE of an area is defined as, you can see, IA minus IS. It need not be IA, IS, any keyword PA, PS like that. So it is IA minus IS. What do you mean by IA minus IS? You can see, because this slide I referred from one of the government publications from India, from their energy center, I took this slide. Therefore, I'll be keeping the same keyword for my presentation. IA, actual net interchange negative for northern region, meaning import by NR. NR means they are referring to one of the example, northern region. Suppose I am speaking about its A's. Let's say A's of a northern region is IA minus IS. IA shall mean actual net interchange. What is IS? Scheduled net interchange. Scheduled power, what is to be exchanged, what is actually being exchanged if there exists a error. That is called as negative, means this is importing. If it is a positive, it is exporting. You can see actual and scheduled. Scheduled is say 10 megawatt, actual is 12 megawatt. Definitely have surplus. Then 12 megawatt is more than 10. Definitely it must be positive. Other way it is 12 is the scheduled, 10 is the actual. It results in negative. That means actual net interchange negative for certain reason, meaning import is noticed by that reason from the other corporation. That is the first term. It is to calculate what is the actual power scheduled, what is the actual power flowing. So I'll take you back to the next previous slide and I'll convince you how this is computed. Plus, there is a bias 10 into frequency bias BF, frequency bias coefficient, that is called megawatt per 0.1 hertz change. This is a factor. We'll see what is this very soon. Plus 10 into a frequency bias in the bracket FA minus 50. Suppose Indian continent is having a 50 hertz as a frequency. 50 scheduled frequency, actual frequency. This difference we call as frequency deviation. Actual frequency, desired frequency. Deviations, on that deviation, what is the bias? Controlling factor riding, that is called area frequency bias. This is called as for every 0.1 hertz drop of frequency, 1 megawatt set point in the generator has to be shifted. That is called as frequency bias coefficient. I repeat back. When there is a load in the particular area, as the load increases, it is natural to experience drop in the frequency. That is called as actual frequency less than scheduled frequency whenever loading is noticed. So this difference has to be worked out, brought to zero. Therefore, actual frequency has to be scheduled frequency. In that due regard, somebody has to initiate a control on generation side so that megawatt output need to be improved. So that is called as area frequency bias, which is a action on the generating side such that for every 0.1 hertz dip in the calculation, every 0.1 hertz dip, 1 megawatt computation increase has to happen. This is how. The other way you think of, load is suddenly thrown off, load is suddenly decreased. What would happen? Actual frequency shoots up. Definitely frequency override than your scheduled frequency. At that time, what you must do? Generator need to reduce their generation. In that due regard, this megawatt has to be a decrement command for every 0.1 hertz rise in frequency. That is the meaning frequency bias coefficient. So it is 10. This 10 is multiplier for 0.1 to correct. This is a value in the scale of 0.1. This 0.1 is converted to unit 1 by having multiplier 10. Hence it is 10 into area frequency bias into actual deviation in frequency. Normally observed frequency, expected frequency. This calculation term results you area's state. Do this area's AC is positive, overall value is positive. What it indicates? This should indicate certain area whose AC you are speaking is having excessive generation. If the A's value of a certain area is negative, what it would mean? This is finding deficit of generation. It need to borrow or it need to reduce the loads. Demand side strategy, load curtailment. Some techniques need to be adopted so that AC is controlled within a specific range permissible. So therefore, ACE specifies, signifies the steady state operation of a particular control area. If ACE is 0, it is a steady operation. If ACE is positive, area is having excessive generation than what it is exactly transacting. If ACE is negative, it is deficit in generation. It do need a borrowing of power or some strategies to control the particular demand such that AC is brought back to 0. That is a scenario of ACE. So their example is given. ACE positive means northern region is surplus and NR internal generation has to back down. Suppose when you are transacting with the neighbor corporation, nobody is in need of additional power. Suddenly, ACE of your state, ACE of your area's calculation at a certain hour is positive. It is to say, burn the fuel little lesser and lesser at the generator. It means generation has to be decreased. If the ACE is negative, you have deficit of generation. What can be done? Internal generation has to increase. If you have a generators capable of increasing their generation, this stimulus is negative means increase the set points. If generators have stalled, kept their values maximum, they have reached their maximum point, then there is no fun in raising the set point. Only thing is you have to borrow the power. That is an indication of ACE. So therefore, area control error and area control area are the important terminologies connected to a control area. Let us go back how this ACE is understood from this diagram. Let us view this diagram again. Here I have automatic generation controller. Just for this automatic generation controller to act on generators, to act on loads, this has to take a decision. This is the computer control of generation. Signals has to go to transmission network and to others. How is that? As the computation comes here, you can go back here. There is a summer block, summation block. Can you see this summation block? There is a scheduled power exchange, PS, scheduled exchange, and you have measurement here. There is a P1, outgoing power. There is a P3, the exchange is going on with the neighbor. P2, P4. These are the exchange with the neighbor corporation. That is called as here IA, actual net interchange. Actual net interchange. What is happening with this area with the neighbor area, which is measured as P1, P3, P2, P4. That is a flow of power outward. Next is flow of power inside of is also there. Outward power flow is summed up. You can see plus to the summer block. It is added. Net power exchanged from this area minus the P scheduled, PS. There in the next slide, they have used IA, IS. Instead, this one of the textbook content refer P. P refers to active power delivery. P1, P2, P3, P4, outgoing power flows. Some of them, it become a grand exchange of power from this control area minus the scheduled interchange. This give you power mismatch. That is the first term. Power actually flowing out minus the scheduled power is the power mismatch. This is what is being computed here. Power mismatch. That is added with the term. What is that? 10BF0, base frequency with the minus, and 10B or beta actual frequency. Actual frequency I have to measure from this area, which is called F actual, and F0 is the scheduled or intended frequency for this system operation, like 50 Hertz for our normal. Then it is the summer block with the 10BF actual minus 10B F0. If I resolve it, it becomes 10B outside, F actual minus F0. So I have to add this, that become a yes. So it become P actual minus P scheduled plus 10 area frequency bias B inside the bracket F actual minus F0. That is the ACE, area control error. If this ACE is 0, AGC no need to exchange signal with the neighbor to increase or decrease, status quo, continue as it is. If AC is positive, it has to signal reduce the generation. Its signal has to go to the generators, decrease the generation, or make something exchanging for your next transaction. If ACE finds negative over here, this is the indication for the algorithm to see to it that whether you can increase the generation of your generator if possible, or borrow the power which you are selling the power, start borrowing the power so that ACE of the area is controlled back to 0. That is the activity of automatic generation controller in a control area. In a control area, the algorithm situated in the control center of a computer works for that. For that, stimulus is ACE. ACE is computed in this regard. Now imagine such a calculation is there in northern region, southern region, western, eastern, northeastern. Then they connect themselves each other with a radiating line. They start making their areas maintained at AS0 first. Then deal with the neighbor corporation. When they are dealing with the neighbor corporation, it is a bounded duty of both the corporation to see to it that areas AS become managed by them without disturbing the neighbor corporations. We look forward called as interconnected operation, pool operation, wheeling of power are the alternative keywords we have to learn. What is that? Let us imagine the northern region want to sell power to southern region. Geographically, they are far away. They cannot drive the power directly to this. They have to route to the transmission line and get it to the region. So they have to connect themselves in an interconnected mode of operation. When there is a borrowing up of power from the southern region and selling up of power from northern region, somebody has to manage this. That is called as central agency. Central agency somewhere in the corporation between northern, southern, eastern, western, and northeastern. They have to design or develop a central controlling agency which will look for exchange of power from one to another. Then in between those states or regions come across the transfer of power are also given an indication these two corporations are on the transaction. Power flow is occurring on these many transmission sections. You be cautious about the transaction because there is a borrowing up of power via the transmission sections of certain path from the which is selling. Other parties which are involved in the mechanism, intermediate, they also get subjected to stress. There could be a fault in southern. That fault propagates through the path to the northern. Like that, somebody has to, that is called as AGC operation, automatic generation controller for interconnected operation. That is the next chapter we are going to understand. We are talking about AGC inside a area which is called as a control area. What are all the functions that is performing to see to that signals are emitted from that controller till the area which they are reaching to balance the area's generation. So therefore, this has to be worked out. So this is about the area. You may have a very good question. Define control area and area control error with a neat sketch or a block diagram. This could be a block diagram which you can take as a reference. You can define what is control area, what are all the components of this control area, how is that AGC function in this area, what is that area control error in this control area, meaning of that, like whatever the expression we have seen, has to be put together. So this picture and these expression meaning should help you to understand and present the content. So A's must be 0 for steady operation. When I want to say interconnected operation is there, one to one, one to one, one to one, there is a connectivity. Then how do you understand certain area is borrowing, certain area is selling, like that? That is the task assigned to Central Energy Control Center, or a Common Energy Control Center, AGC, will keep request bidding. Who all can sell the power, who all can buy the power, borrow the power. There will be a power trading concept. So somebody who is having excess generation, keep bidding. This is the megawatt available excess from this hour of a day till this hour of a day, or this hour of a month, certain, like that. The corporations which are shortfall of themselves, they will demand, I need so much of megawatt for a certain duration and to a certain duration. Who can supply this? Like bidding and following up of activity done by the corporations agreed upon. That central AGC will respond to those who want to sell, to those who want to borrow. That will make the contract between them and signal those areas to transact. When it is a transaction, till that A's of a certain area which is a shortfall is always a minus. A's of a certain area which is selling is a plus. Till the A's of a negative area become a plus or a 0, transaction keeps working. For that, how much is the megawatt exchanged has to be paid for that. Then transmission mechanisms which are being used, for which they have to pay for service charges. Transmission lines connected to that megawatt exchange total, then how long it was in service, 6 hours, 8 hours, 1 week, like that. That duration, megawatt and service have to be paid for actual transient. That is done by Central AGC. Keep a record of books for every month or every duration that transaction is discharged. This is the amount you have to pay. This is the amount you have to exchange, like that. Trading is maintained among them. So for that, input again is area control error. So therefore, altogether for a steady operation, A's of an area matter the most. One more slide I have, which again defines what is the A's. The area control error is combination of the deviation of frequency from nominal and a difference between actual flow out of an area and a agreed flow. This is a stimulus. It is actually indicator. If it is negative, there is a shortfall. If it is a positive, there is an excess generation. So that is again put by another equation I have put here. This I have taken from Wood and Uhlenberg presentations. Is equal to actual power which is flowing on the tie lines minus the scheduled power from that area plus the 10, the constant beta area frequency bias into F actual minus F delta F, called as deviation. So ideally A's must be 0 because load is changing. It is impossible to maintain A's 0. Hence it's called, because the load is constantly changing, each area must constantly change its generation to drive the A's towards 0. A's has to be maintained 0. To keep the A's 0, the generation set point in the generating area has to be dynamically monitored. Now you look forward. We have learned economic scheduling. Economic scheduling was just a concept dealt. Scheduling certain generator for a certain megawatt, taking care of their production cost. No matter how that power is routed, who is absorbing, like that. It is just an economy in scheduling the megawatts on a certain generator. Then we studied optimum power flow, routing the power to the end user in a very optimal manner. Now look into this. All these factors have to be taken care. For a certain change in demand, your set points are being modified. If set points are being modified, again the entire computation gets deviated. So you require very dynamic corrections into your calculations. Therefore, it must be seen very, very seriously. Hence, concern to the economic operation optimization, it is very serious. So therefore, A's of an area must be maintained 0. Then, how that AGC calculations are being done? Again, certain A's of a locality, measured frequency, standard actual frequency is taken as an summer block, frequency deviation, and a area frequency bias. This is called as correction required for every 0.1 hertz drop. What is the megawatt increment you should do? That is called as the area frequency bias, and measurement of P1, P2, P3 tie line power and scheduled exchange you subtract from that. That you take and that you make as a method. This is a mathematical review. I have just taken whatever actually this first term, P actual line on the tie line and schedule. These two are together put in the lower half, upper half is frequency. This is from again some other presentation I have picked for the easiness of understanding. So it does the calculation. So you can see it is again in the text, control must be also drive the generating units to obey the economic dispatch in addition to pushing the frequency and talent power to 0. So I was speaking. It is not that only economics I should see. I should see operational aspects of the power system carefully. Frequency deviation had to be brought 0 and economy you have to see carefully. This is how it is being worked carefully. And A's should be brought to 0. It is a composite signal, mixing up of tie line power and frequency. A composite signal is used to signal the generations and make the control. An automatic generator control implement at generator side, how it's being done. A's signal should be kept moderate in size. A's is influenced by random load variation. Standard deviation of the A's must be small. It means when I want to monitor the steady state operation of the power system, automatic generation controller in a controlled area should be within certain A's. How can A's be so large in positive? How can A's be so large in negative? Is it permissible? Definitely no. A's at plus side, A's at minus side should be certain percentage of the max capacity of the area. Suppose it is say area capacity is 100 megawatt. It can be 5 to 10% of the capacity at the upper side, lower side. A's should not cross beyond that percentage which is defined by the corporation. If it is going beyond that, it is not possible for the corporation to manage that. Hence, it is that A's must be specific by plus side and minus side. And A's should not be allowed to drift. It means once there is an A's is noticed, error is noticed. How long you keep error observing like that? A's must be addressed immediately. What A's indicates? It's a requirement either to increase the generation or the change in load, or there is a load lowering, reduction, decrease the generation. This has to be acted upon immediately, yes or no? Otherwise, unnecessary burning up of fuel will take place. It is not an economic operation. In that due respect, once the A's is simulated or brought within a minute of that, there should be a control action initiated in the American Power Corporation. In every 1 minute, within a minute of occurrence of a A's, there should be a control action initiated in the American Energy Corporation. Similar is practiced. Then, what should be the other way of A's then? A's must be 0. At least once in every 10 minutes of time stamp. Suppose you are operating a power system, 0 hour, 0, 1, 2, 3 hours if I make, 24 hours at a slot if I make. And in each hour, I classify it as a minutes, 0, 10, 20, in terms of tens minutes. Every 10 minutes of observation, is whatever it is a plus or minus, it has to become at least once 0 in every 10 minutes. It means A's cannot remain plus 10 minutes and beyond. That is an observation and requirement of a design. It means if ACE is constantly plus more than 10 minutes, it's the indication that current actions are not suitable for the ACE to bring zero. So there must be a control action initiated. Then ACE shall not be more than certain amount plus side, certain amount minus side. They are the one I am trying to configure over here. Good design of an automatic controlling area should have ACE value for plus limit, minus limit must be specified. ACE should be immediately addressed within a minute of its occurrence, and ACE should become zero at least once in every 10 minutes of stamp of time. Then this ensures the design of automatic generation controller in a area has really gone well, doing perfectly. That is a requirement called as characteristics of ACE. So this should be seen carefully about this. Then once we look to the aspects of generation and connected control, let us view second part of that. How is that fuel input control on the turbines acted upon? Therefore, we have speed governor concept. Speed governor is maintained, or it is used to operate the valves connected to the input fuel to the turbines. The turbines were driven by a suitable fuel, maybe hydro, maybe a gas, or maybe a oil, something like that. Depends on your locality and the resource. These governors will definitely operate on the mechanisms to operate the valves, modulate the valves such that such an displacement of the valve control the input fuel to the turbine, as and when there is a change, turbine accelerate or decelerate according to the need, and your required megawatt generation and frequency controlling will be in picture. So therefore, for that we require governor. It's called as speed governor, and it is necessary that it is not only being done, it requires certain components, which is like some relays, servo motors, pressure or power amplifier, which all together in interconnection act upon the point of control to see to that the control is exercised to meet your requirements. Then how it is being done? It is being done with certain observation. You can just see this diagram. Let's see, before going to the theory portion, let us see this diagram. This diagram is having a generator. Generator is developing a power PG, and it is connected to grid. PG is being pumped to the grid, and mechanical input to which is a steam turbine. Steam turbine is driving the generator, and generated power PG is pumped to the grid. For this, mechanical supplement is PM, power mechanical. Then that is obtained by steam turbine. Steam turbine is being operated by steam valve input control. There is a steam valve and there is a control valve, and steam continuously flow and make the turbine to run at a certain RPM as desired, so that such a RPM suitably develop a megawatt and frequency required. So input fuel, it's a shut-off valve, which is a main valve, and a control valve. In control of that, there is a flow in the line to the turbine is managed, and RPM of that is fed back to the controller. Then I have a governing mechanism. Now I am making you understand how this governing mechanism come into picture. The governing mechanism govern the opening and closing up of the valve in requirement of the actual speed of this. Suppose actual speed is say 1500, it has to open the valve to see to that speed of the turbine is 1500. As and when there is a loading phenomena, definitely deceleration is noticed. To see to that certain deceleration is again pop-up valve have to be opened, so that there is an excess fuel which will manage the RPM back to the steady, and its frequency is again normal. For that, somebody has to act on. That is called governing mechanism. So speed governing mechanism take reference speed. What's the steady speed for this? Reference speed. Then it require input from the grid. What is the power it is flowing out or power it is developing? And what is the actual speed it is possessing right now. So using the reference speed, actual speed, what it is developed or developing is taken as a control input for that. According to that decision taken inside, it develops a displacement command. That displacement command make the valve whether to open or close depending upon the decision. If there is a slowing up of the turbine, means the RPM has slowed down, frequency has fallen down, we have to shift the frequency back to steady, then required shift in RPM, nothing but input increment has to happen in the flow. That has to open the valve more and more so that input fuel adjusts the RPM as required for the frequency. So this is dynamically done by the governing mechanism. That's what we are speaking. The governor is maintain the fuel input to the turbine as appropriate to generate required power. And it requires so many control mechanisms associated. Then what are those things? It requires, look to the next diagram. Suppose fly ball mechanism, fly ball governor. If I view, what role it require? It require the valves, what I am trying to operate here. This valve opening, closing command has to be there. It's called as signal, open, close. This arrow shoots up. Then how to set the reference speed? There is a reference speed setting point. Raise or lower the set point. See, this is a set point control. Then this require inputs, input from speed feedback. So this is the mechanism. Speed of the governor is fed by a spring and ball, fly ball mechanism. Then this keeps on continuously revolving, and that revolution make the mechanism to act on. You will see it very soon. Then this fly ball mechanism require speed feedback network, set point network, then actuations to control the valve. Here I have shown an arrow directly. It is not the reality. It signal hydraulic amplifier, hydraulic actuators. Hydraulic actuator will push or pull the gates of the valve so that input fuel is managed. That is by hydraulic mechanism. Then to function in overall, it requires these many. Fly ball speed governor. I am speaking about this entire connected mechanism. This is the heading of that. This is a mechanical device which is speed sensitive and directly adjusts the valve opening via the linkage mechanism. It senses the change in speed or power output and appropriately initiate valve opening or closing. Can you see this? The purpose of governor itself. So this mechanism, fly ball, these are solid circles which are shown to you, is a balls, heavy metallic balls. Like an example, if you have a thread, if you have a ball or a heavy mass connected to the thread and start rotating around us as a whirl effect. If the RPM is slow and slow, it is falling to the narrow to the ground. When the RPM increases, definitely the thread and that mass automatically become equal to your shoulder level and it will raise above. That's called as synchronous and super synchronous like revolutions. It means this fly ball mechanism is coupled, linked to the actual RPM. This actual RPM, what is being connected? This is connected over here. This is going to drive this. This is going to rotate. As it rotates, the spring and the fly ball stretch outward. As they stretch outward means there is a very high speed of operation. They will be centrifugally moving outward. If the RPM of the shaft is low, automatically spring contrast means it becomes vertically elongates. It open vertically upward. When there is a high speed, it will make contract and make it horizontally widen. Like a heavy mass connected to a thread and make it rotating around you. Like when you are a child, we will be playing with that whirl mechanism. A stone, if you tie to a thread and make it rotate around us, when you have a low RPM, naturally that thread and stone connected will be rotating around us at very inclined to the ground. When you make a RPM of that thread faster and faster, definitely that stone and thread make themselves aligned horizontal to your directions of rotation. In that way, the same mechanism, fly ball mechanism functions. These two flying balls connected by a spring driven by a speed of the actual turbine RPM. When the RPM is at steady state, this is at steady position certain. If RPM is higher and higher, these two balls move outward and the mechanism is pulled down. This is pulled down and it is elongated along the horizontal axis. The RPM is low, the spring will pull them towards center and this will elongate vertically. So this contraction and elongation will make this lever to act on a hydraulic mechanism and to open and close the valve. That is the functionality. We will see it still better. I am speaking about how this fly ball speed mechanism is making one of the constituent part inside this governor I am speaking. This is a mechanical device which sends the speed and power. Accordingly, the actions of this is nothing but displacement of position. This displacement position will act on the valve. Then we have linkage mechanism. The linkage mechanism is nothing but the steel rods from this point to next point to another this way. For this to understand, let us imagine a conventional bicycle, not the one which is having the latest bikes where you have brake mechanism with a wire. Now imagine a bike with a rod from the handle. When you operate the brake mechanism, they move, lever will operate upward, then it is tangentially transformed into lower, linear, and that will apply brakes on the rim. Like that conventional bicycle, if you imagine, this is like a rods, threads move like this way. So whenever you have displacement acted here, that displacement do modify here also. It means this linkage nothing but transmission of displacement from point of control to the point of action. That's called linkage mechanism. This transform fly ball movements. These movements, upward shift, downward shift, whatever is happening according to the speed of the turbine, these linkages, these displacement, we call it as a power displacement, have to be transformed to make that action on the valves. That you can see on this diagram. I have another diagram with the arrows I have marked here. Clearly we can understand that. Okay. Meantime, let us look into this. Linkage mechanism is the lever, rods, and the rotating contacts here. These are the one which I am calling upon. These are used to transfer the movements of this feedback network and set point to the valve and to control. Then hydraulic amplifier. This is one I am speaking about. Hydraulic amplifier. Is it possible to have any variation, increase, decrease set point? I do by screw and nut mechanism. This is like a screw and nut. If I rotate the nut, it may go up, thread it opposite, it come down. So by having this done, raise the speed set point, lower the set point. Like that, I can adjust this set point. This is called reference speed set point. Reference speed set point is done by this mechanism. That reference speed, actual speed, the error is transformed forward. That's what mechanically is being done. So therefore, to transfer the error, that error has to, whether the error is to open the valve more and more. How do you operate very heavy mass with a manual mode? It is not possible. Hydraulic amplifier, actuators, piston and blocks. These are the one which will make the small, minute, micrometric displacement into actual displacement of the valve for the power increments to occur. That is being done by hydraulic amplifier. It is a hydraulic servo motor interposed between governor and the valve to build mechanical forces strong enough to operate the steam valves or water gates. Imagine this is how. This is the water flow or gas flow. Here you want to make the valve close or open. There is a huge load on this. Against the load, it has to either close are open. Opening and closing is not by manual. This hydraulic piston will make it to either go upward or downward. This mechanism I am speaking as hydraulic amplifier. We'll come back to this soon. Okay. So hydraulic amplifier or a servo motor is an interface between the speed governor and the valve mechanism for the appropriate displacements of power. Then speed changer. Speed changer is the one which I was speaking here. Set point. So it is required to set. What is required? Suppose RPM is 1000. By having it graduated, what is the mark of 1000, 1100? You have to set it properly so that there is a proper grading of requirement over here, and accordingly that required set point, the speed reference, is cross-checked by actual RPM and actual calculation. That is done by set point, actual feedback RPM. Error is making this lever to either bend down or go up. So depending upon the fly ball mechanism, it is vertically elongated or horizontally elongated. Depending upon the actual speed, this input is displaced at this point, either to pull it down or push it up. So I'll show you in the next slide. That is transformed to hydraulic actuator. Hydraulic actuator will make the displacement of the piston with the high pressurized oil rushing inside the block, make the levers to displace the gates, on whose displacement input fuel inside the pipes or penstock pipes or flow pipe is managed properly to accelerate or decelerate according to your decisions. This is the mechanism. For that we require speed changer also. So the constituent part of speed governor or fly ball mechanism to have actual RPM feedback, linkage mechanism to link this set point and actual RPM to the hydraulic amplifier to open and close the valves, and hydraulic amplifier actually on the displacement of requirement, open or close the valve, high force or torque is required, that is being done by this. Then speed changer is the input set point controller. So all these things are completely mechanical aspects, which this block diagram shows. Simple outline. This shows little closer to the mechanical set points. So therefore, this is again view. You may have a good question. Explain fly ball governor with a neat sketch. Explain the working of fly ball governor or a speed controller. It may be a question. Then you may need to understand these to draw such a diagram. Fly ball speed governing system. Again, I am making it magnified view for one more look. Here I have some arrows marked on this slide. You can see here there is a input fuel pipe to the turbine, whether it is a steam or a water. It is an input fuel. In between I have a controlling mechanism. This lever on whose upward moment the valve or this opening of the pipe is blocked. Block, open. You can see this conical structure go and block the flow. It means reduce the flow outward to the turbine. So input fuel is closed, input fuel is opened. This vertical up and down movement need to be managed by hydraulic amplifier, because against the heavy mass it has to act. Therefore, it is not by ordinary control. It must be hydraulically actuated mechanism. This hydraulic actuator requires cylinder, manifold block, pistons, connecting lever. This is shown here. You can see this imaginary block here. This is block is having main piston. Main piston, connected rod. This connected rod, suppose if we just imagine this rectangle box, this box. Just imagine this box. See that there is an oil filled in the upper white space here, lower white space here. If imagine oil is evacuated from this side, oil is taken out, oil is rushed from bottom. If oil is rushed from the bottom, piston goes upward. If it goes upward, it is closing the valve. Suppose oil enter from the top and taken out from this side. Oil enter inside the block, piston block, it will push down. Then you are opening the valve. That is the gist of this. To open more and more, this piston has to come down. This main piston has to go down. Oil has to enter from the upper block. If it has to close the valves, piston has to go upward, then oil has to enter from the lower path here. That is the gist of this. Main piston, upward movements make the valve to close, lower movements make the valve to open. Proportionately, it should happen up, down as per the requirement automatically. Hence, it is done by a hydraulic amplifier mechanism. For this, for this, oil to enter upward via or lower via, I have another called as a pilot valve. These are called as a pilot valve. This pilot valve is having another, like this cylinder, another vertical arrangement. There are two piston blocks here. Can you see this? Horizontal strips here, which is on a vertical connected rod, the strip and strip here. So these are having a minute air gaps here. Suppose this point D is moved little bit upward, a small micrometer upward. Then high pressure oil, which an arrow is shown here. High pressure oil can enter this path and make the piston to go down. Then this will open down. So to open more, oil must enter. I have mentioned here. Opening means oil must enter to upper part. Then this point must be downward. D has to come downward. If D point, D has to go upward. Sorry, D has to go upward. When it go upward, there is a opening up of gap here. Once it go upward, oil can rush inside this and make the piston downward. Then there will be entry of more fuel to this. The opposite side. Suppose this displacement is higher, you want to close it. Then you must see to it that this point D has to come down. I have put an arrow. Left side arrow say close the valve. Right side valve say open. It means open, close is put by left and right. Let's say to open more and more, left side I consider. If this displacement is upward, oil enter from the top. Piston is pushed downward. So make the more fuel to go. Then this point D is pulled down. Close this from probably open this way. Oil enters in from the lower port. It makes the piston to go upward. Upward means close it. This way, this hydraulic amplifier functions. The movement of this is automatically from point D. Point D sends whether it has to be closed or it has to be opened. That is acting on these blocks, pilot valves. This point D is again controlled by point B. Point B is nothing but actual speed feedback. This is called fly ball mechanism. And for this, reference set point. We'll see very distinguished way of understanding this. So we have A, B, C, D, E. There are 5 contact points. We call them as power displacements. So these power displacements are acted upon this flow. How it comes, you can see. This is called as speed changer or set point controller. Having it appropriately adjusted like a nut and bolt, you can set it either increase or decrease according to the position mentioned. If you go upward, it is the reducing set point. If you come downward, you are raising the requirement more and more. So that is being marked and that speed changer. That adjustment will make this point either go downward or go upward. So this point A is directly controlled by operating this lever, this nut-like mechanism. When I bring it upward, A goes upward. When I pull it down, thread it down, it will go down. So this is the power point or a contact of displacement of speed changer. Next point is B. A, B, C is a single lever. It's a single lever from A to C. B is a flexible point. B will shift it upward or downward micrometrically. A is fixed. You have set it down or set it up, lock. This A will not move further until you touch this. Let's say you have kept it for certain RPM. Then this A will be acting on C. A requirement is acting on C via B. B can shift it like a cantilever. From this point, C is moving either cantilever wise upward or cantilever wise downward. That is done by B. B will pull or push like this way. So it is making upward or downward movement at center of this rod, so that C is put up or put down. Let's say B is acted by another linking rods. These are all the linking rods connected by flying heavy balls, spring acted balls, and another ball is connected here, and it is connected to the actual RPM. For this, what I can say, imagine the particular RPM shaft feedback. Shaft RPM is connected to this directly. Revolutions per minute, what the shaft is executing at the turbine, it is directly brought and it is going to rotate. This is actually a rotating object. This is going to rotate, as and when rotation is very, very low, definitely the spring mechanism connected to fly balls will contract, bring these balls closer to each other. Vertically, it will move upward. B will be shifted upward. If the speed governor's actual speed of the turbine is very high, then these two balls will widen themselves horizontally, like your whirling effect. When this widens up, B is pulled down. B is pulled down. C is also pulled down. So therefore, point C's operation, A is transformed to C via B. B makes the shift of C upward or downward depending upon the actual RPM of the turbine. Therefore, if the actual RPM is very, very low, let's say upward move means low speed. I have put an arrow here. When the turbine is very, very low RPM due to loading effect or some problems, RPM is reduced, means this fly ball mechanism contract horizontally and make it vertically upward shifted. Then B will lift up and C will also lift up. A is shifted at C by B. It will go upward. If this go upward, definitely point B also go upward. You can just see. When it go upward, definitely a micrometric movement of wall operation has to become oil to enter here. You can see when it go little upward, there is an opening up of valve here. Once it go micrometric upward, high pressure oil will rush here and make the piston go downward. When it go downward, you can see downward movement is observed. Open the valve. This valve opens further, higher fuel will rush to the turbine. So therefore, this piston has to go micrometrically down when there is a dip of this point, and this point will move upward because C has moved upward, D has moved micrometrically upward. There is an aperture opened here. Because of that, there is a high rush of oil, make it to go down and make the opening of this one. This is how, this is a mechanism when there is an deceleration of RPM at the turbine. Suppose other way it could happen. Working mechanism ensure suddenly RPM is very high. You can see this block, I move this arrow. When there is a high speed of operation, whirl effect will make this fly ball go apart, horizontally it will stretch outward, and B is pulled down. B is pulled down and C is also pulled down. Definitely you will find more and more pulling down mechanism of D. D pulled down means you will see high rush of oil from the lower port will enter this block, make it to go up. You can see up means close the valve. So these arrows you consider. First arrow, first arrow, first arrow, first arrow concept. Second arrow, second arrow, second arrow, second arrow concept. When it is a low speed, it is vertical shift. C shifts, B shifts, and D shifts, and oil will enter from oil will enter such that there is an shift of open of valve so that higher RPM is observed. Suppose RPM is very, very high, then this is elongated horizontally, then it is downward. Downward means this C is also downward, D is also downward, oil enters from the lower part, then definitely it has to be managed. So therefore, you should see to it that carefully. When is that high speed, low speed is observed hydraulically. These gates were opened. That's called as a fly ball speed governing mechanism. So for me, when you want to explain it, the fly ball speed governing mechanism is as shown in the diagram. The speed set point is set a point at A, point B, C, D, E are the power displacement points. This actual speed feedback is taken from the speed governor. The moment of this point B will be pulling down the A at C whenever this is at a very high speed, and C is shifted upward whenever B is very, very low, means low speed. Then accordingly, C is acting on the point D to see to that pilot valve is opened and closed for the suitable displacement of the main piston, such that valve opening and closing as per the need occur. This has to be done synchronously in the mechanism. That is the purpose of fly ball speed governing mechanism. So therefore, kindly consider these arrows carefully, which I have put for your reference, which will be helpful to you. So that is a need. I cannot operate as and when there is a speed fall. I cannot open the valve manually. Hydraulically, I will make the valve gates to open further for the higher fuel to go. And there is an RPM very high. Load is suddenly removed. Then RPM shoots up. Definitely, I have to close the valve. I cannot rush and do it immediately. This has to be synchronously connected to a working mechanism of hydraulics, so that that hydraulic mechanism with its impact on gate and opening mechanism makes the things to happen. This is how fly ball speed governing mechanism functions for control of input fuel at the station. And definitely I have the same operation. I can view this way. Modes of governor operation. Here we have seen how is that governor, fly ball governor, function to open and close the valve according to the actual RPM of the shaft or turbine. How this mechanism makes the things to happen. Now, how it operates, you can see you require a turbine for which you require steam or a water. There is a valve. This valve has to be controlled. Then turbine drives the generation. You require to see to that hydraulic amplification and speed changer is required. This will act on the valve so that input fuel is controlled to the turbine. For this hydraulic amplification and speed changer, you require so many requirements like electronic hydraulic converter. You have to sense, process, and primarily amplify if required, and make the hydraulic amplifier and servo motor to function. This is the connectivity. So therefore, to control the turbine RPM, no doubt you require a hydraulic amplifier and speed changer. For that to take a decision, you require converters, electronic and hydraulic converter or a controller, which require sensory like data of speed, megawatt. It has to be sensed, processed, and stimulus of that or output of that become stimulus to the converter. Converter will initiate the hydraulic amplifier to displace the valve position. This way, a simple speed load controller. As the load changes, speed definitely falls. Speed management has to be done by speed load controller. Again, we have electronic hydraulic controller, which is electronic hydraulic. This is an interface. This is an interface of measure of speed and load, and these sensing elements will process and act on the hydraulic mechanism so that amplification of the signal and controlling of gates takes place here. That's called electronic hydraulic controller. This in raw terms look like this way. You should have inside this speed controller. When I have a speed and megawatt input, how do you think inside? What is happening inside? Speed reference set, speed actual. I compare. This is processed in the speed controller. Then actual required reference power, what is to be generated, what is actually thrown out. This power mismatch is worked out as load controller. These two individual controller inside make the logic what should happen, whether to open the wall or to close the wall is a decision. It means to say it is actually speed load controller using electronic hydraulic amplification controlling, wherein speed comparison for the speed part of the mechanism and power comparison and control for the load aspects of that to be combined as a decision taking process. Control logic